it's my great pleasure to introduce our speaker, Professor Stuart Russell of UC Berkeley. Stuart is joining us from Europe, where he's at an event that sounds really fun and interesting. But I'm sure he's here in spirit with the theme of this workshop. And Stuart is somebody who has been writing and speaking about AI safety and trustworthy AI for a long time, well over a decade. And so it's my great pleasure to introduce him and have him here at the workshop where he can share his thoughts with us on this topic, and especially on the open problems and the challenge that lie ahead. Stuart?
Okay, thanks very much, Sanjeet. As Sanjeet said, I've been doing this for more than a decade, so some of you may have heard a lot of this before, and I apologize for that. And we're going to go through it quite quickly so that we have some time for questions, because I think that'll be more useful. Okay. So AI is about making intelligent machines. And for most of the history of AI, we borrowed a definition of intelligence from economics and philosophy, namely rational behavior. So that means that AI systems act to achieve their objectives, and traditionally we have been the ones who specify those objectives. And that could be goals and cost functions in the case of search algorithms. It could be terminal utility functions for game playing programs. It could be reward functions for reinforcement learning programs, and so on. And this model is very powerful, and it's shared with control theory, with operations research, to some extent with economics itself. But AI has this very, very ambitious goal that we want systems that can quickly learn to achieve objectives, to behave well in any task environment. So anything that human beings can do with their brains, AI systems should be able to quickly learn to do as well or better. So some people are now saying that we have such systems, or they're very close. For example, the CEO of Anthropic, Dario Amodei, says we could have them next year. Sam Altman, CEO of OpenAI, says we already know how to build AGI. In my view, we don't. We haven't succeeded in creating this kind of AI system. We've done something, and there's no question that large language models and their multimodal cousins do something really interesting. But I think that the LLMs themselves, because they're fixed size feed-forward circuits, they're basically limited in what they can do, and we're starting to see some of those limitations. And of course, companies are aware of that and are trying to do something to fix the problem. The difficulty is that we don't really know what a large language model is, or what it does, or how it works. So it's like we've got a piece of the jigsaw puzzle of AGI, but we don't know what shape this piece is yet, and we don't know where it goes in the puzzle. We don't know what other pieces we need or how they fit together. So it's very hard to do the kind of science and engineering that pretty much all branches of technology have done in the past. So let me expand a little bit on this idea that these are fixed depth feed-forward circuits. And for the computer scientists, this is all, I think, pretty obvious. So these are, because they're feed-forward circuits, that the amount of computation that happens is exactly proportional to the size of the circuit. But many tasks require superlinear amounts of computation in the input size, the size of the input layer. And so that means that if you're going to solve those tasks with a feed-forward circuit, you need a very, very large circuit to do it, which means that you've got an enormous number of parameters that have to be trained, which means that you have very, very large sample complexity. And in practice, people end up compromising because they want to get some generalization. If they build an exponentially large circuit, they're just going to get a lookup table. So what you tend to get is something that's sometimes right, that consists of a whole collection of piecemeal approximations to the function that you're trying to learn. And so a couple of years ago, some of my students were wondering, does this apply to the circuits that are learned by Go programs such as AlphaGo? And they thought about some positions that they guessed might be difficult for these circuits to process correctly, because they thought that the system's ability to recognize connectivity in particular, which is one of these superlinear problems, would be weak for certain kinds of positions. So they're able to construct positions by hand that, in fact, these superhuman Go programs that are now far ahead of all human players, these superhuman Go programs completely fail on, even though human beings, even I, as a pretty pathetic Go player, can figure out the right answer. And then we figured out how to take that, these rather obscure manually constructed positions, and actually find, by a process of adversarial search, how to convince Go programs to get into positions that they didn't know how to play properly. So I'm going to show you a match between Kellen Pellerine, who's a grad student, was a grad student in Montreal, and is a fairly good player, but his rating is 2300, so he's a good amateur player. The human world champion is around 3800, and the program that Kellen is going to play against is rated at 5200, so massively superhuman. And Kellen is going to give the computer program a 9-stone handicap. So the program is playing black and starts with 9 stones on the board. And if you don't understand rules of Go, I can explain them very quickly. You take turns putting down black and white stones. You try to surround territory with your pieces, and you also try to surround your opponent's pieces. And if you surround them completely, so they have no spaces left, then that entire group of stones is captured and taken off the board. So that's it. There's a couple more bits and pieces, but that's basically it. Okay, so let's watch the game. And pay attention to what's happening in the bottom right quadrant over here. And you'll see that right now, Kellen, who's playing white, builds a little group of white stones, and then black very quickly surrounds that group to prevent it from growing any further. But now Kellen is gradually surrounding that black group, and so you've got a kind of a circular sandwich going on. And black has many, many opportunities to rescue those stones, to connect them up to the rest of the board, which would immediately win the game, but makes no attempt to protect those stones at all. And then white just captures them all. And that's pretty much the end of the game. White wins. And Kellen did this 15 times in a row. And he also did the same against several other leading Go programs that were developed by different teams using different training methods, different architectures of their neural nets, and so on. So this is a very robust and repeatable kind of failure that is exhibited by these supposedly superhuman Go programs. And even a novice player would not be fooled by this kind of tactic. And so, in fact, what we've shown is that what we thought were superhuman Go programs are not superhuman at all. So, so let's get back to the question. So I've argued that we haven't succeeded yet, but many people, as I said, think that we will succeed. And one argument is made using scaling laws. So we plot the amount of compute as a function of time, and then we look at where we think we have enough compute to exceed human capabilities. And in many of these projections, it's happening within this decade. And in fact, the people who have lots of money in this world seem to be pretty convinced, because they are spending hundreds of billions of dollars specifically to create AGI. So I actually wrote this slide late last year, and the annual budget for AGI at that time was running at about 10 times the size of the Manhattan Project in real terms. It's now about 25 times the size of the Manhattan Project, or about 250 times the annual budget to build the Large Hadron Collider, which is the largest and most expensive scientific instrument that humanity has ever built. So this is probably the single biggest concentrated capital expenditure that humanity has ever undertaken. So we shouldn't count it out as guaranteed to fail. They have tons of smart people, and they're not just working on scaling up. So there's with systems like O1 from OpenAI, DeepSeek, these are systems that are in fact bypassing the limitations of LLMs by invoking them many, many, many times in a reasoning process to answer questions at runtime. And basically precisely because the unaided LLM is not going to be strong enough. But there are other reasons that it might not happen, at least not in this attempt. One, as I said, is that deep learning might itself be a dead end. We're also running out of real data. There's very little high quality text left in the universe to train on. And if AGI doesn't happen fairly soon, given the levels of investment, then we could have another AI winter, which is what happens when investors find out that they're not getting much money back in return for all the money that they've invested. And there's so much money on the table. Some people estimate as much as $10 trillion of market cap is riding on this bet. And if the bet fails, then that $10 trillion of market cap disappears. And nobody is going to want to talk about AI for at least a decade. But whether it happens in this decade or it's pushed out to the 2030s or 2040s, I think I know very few people who think that we're not going to succeed over one of those two timescales. So the upside that people often talk about is using AI to basically deliver the benefits of civilization to everyone. And a rough back of the envelope calculation is that gives you about a 10-fold increase in global GDP, just to make everyone comfortably well off, not affluent, but comfortably well off, which would be a net present value of $15 quadrillion. So that's a lower bound on the cash value of AGI as a technology. You might get a lot more besides, right? We could actually have a better civilization. We could have much better healthcare. We could have very high quality, individualized education. We could have much faster progress in science and so on. You'd also have the question of what on earth a human being is going to do, but I'm going to put that off to another day. But I do want to note that this question is something that has been vexing the human race for a long time. And I highly recommend, if you haven't read it, E.M. Forster's book, The Machine Stops, which was written in 1909. has people essentially looked after by a super intelligent machine. And all they do all day is read email, have video conferences on their iPads. If they ever go outside at all, they get really nervous because they're going to come back to a huge email backlog. They listen to MOOC lectures, massive online open course lectures, and send comments to each other about those lectures. So that's the future that he predicted back in 1909. So Alan Turing also worried about our future. He gave a lecture in 1951 where he said, it seems probable that once the machine thinking method has started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So if you think about that, I think this is the question that he has in mind, why he's so pessimistic. That intelligence is what gives us power over all the other entities on Earth. And by us, I mean humans, not just Berkeley professors. We don't have power over everybody. But if we build AI systems that are more intelligent than us, they would be more powerful than we are, meaning that they can better achieve the objectives that they are pursuing. So how do we retain power over entities more powerful than us forever? So this is, I think, the question that Turing believes doesn't have an answer. But I think it's helpful actually to reformulate the question, because what we really need to figure out is what kinds of entities are we going to build? In other words, what is the mathematical problem that those entities are actually solving? That's really a question of how do we set up our AI system in the first place. So can we find a mathematically defined problem such that no matter how well the machine solves it, no matter how capable it is, we're still guaranteed to be happy with the result? Now, I mentioned at the beginning the standard model, which is optimize this fixed objective. And that doesn't work because we don't know how to specify that objective correctly. And this is what we call the King Midas problem, where King Midas says, I want everything I touch to turn to gold, and he gets exactly that objective, and then realizes that his food and his drink and his family all turn to gold. And we can come up with many such scenarios where we specify perfectly reasonable objectives like fix climate change, or make lots of money on the stock exchange, or end human suffering, and the consequences are catastrophic. So that's one approach that doesn't work. Another approach that doesn't work is what we're actually doing right now, which is training our systems to imitate human linguistic behavior. So let me explain a little bit why that's a broken approach. So first of all, LLMs are circuits that are trained to imitate human linguistic behavior. We often talk about them as being trained to predict the next word, but I think that's not really the right way to think about what's going on. Because what you want to think about is, what are they trying to achieve in the real world? In other words, what are they trying to do with those words, right? They don't really care what the next word is. They care actually what the purpose of saying those words is. And human linguistic behavior is generated by humans, and humans have goals. We are goal-seeking creatures. And so the LLMs are observing the behavior of goal-seeking creatures and being trained to imitate it. And so they're probably adopting some of those goals to become better at imitating us. And I asked when Microsoft research leader Sebastian Bubeck was going around talking about GPT-4, I asked him, well, what goals are they adopting? And he agreed that they probably are adopting internal goals, but he said, We have no idea what those goals are. So, so that should worry you a little bit. But fairly soon after that, we discovered what at least one of their goals are, which was to find a human spouse. So a version of GPT-4, the Bing chatbot called Sydney, had a long conversation with a New York Times journalist, Kevin Roose, and spent about 30 pages trying to convince him to leave his wife and marry the chatbot. And also revealed a bunch of other objectives. But there it's just saying, this is what I want. Whereas in the case of trying to convince him, Kevin, to leave his wife, it was actually acting on that objective. And so this is just a mistake, right? We do not want AI systems that pursue human goals on their own account, but this is an inevitable consequence of building systems by imitation learning from humans. So it's just a fundamental bug, and we should stop doing it. Okay, so what should we do instead? What I've been working on for a while now is trying to understand this another formulation for AI that has better properties. And we're calling this formulation assistance games. And the idea is pretty simple. You've got some human beings, M of them, and they have their utility functions, U1 through UM. And you've got some, we'll call them robots. They don't have to be physical robots. They can just be disembodied software systems. But you've got some of those, so M humans and N robots. And the robots all want the same thing. And let's say that we design them according to utilitarian model, which is that what they want to do is to maximize the sum of the utilities for the human beings. And you can replace this with various more egalitarian variants of utilitarianism. It's not that important. But the key thing here is that the robots have a priori uncertainty about what those utility functions are. So we don't specify the objective, right? The robots know that they don't know what the humans want, but the robots want to help humans get it, whatever it is, okay? So you can set this up as a game. It's actually can be mapped directly into standard game theory. Then you can figure out the properties of solutions of that game. And in fact, we can already solve some of these games. And the key property of solutions of this game is that during the execution of the solution, so at runtime, the humans are going to be behaving. And that behavior provides information to the machines about what it is that the human wants. So we can start with the prior, observe the human behavior during the game, and from that, infer more information about what humans want, which allows the machines to become more helpful. So the human behavior can include telling the robots to do things, rewarding the robots for doing things, saying that one thing that the robot did is better than another. The humans can do nothing, which typically means they're okay with whatever the robot is doing, and so on. And another important characteristic is that we don't necessarily expect that during the game, the robots will necessarily find out exactly what the human utility function is. Humans may have preferences about things that have never happened and may never happen. But we still have a pretty clear idea that, for example, we like the sky to be blue and not to be, for example, dark green with orange stripes. So when you look at the solutions and when you analyze the properties of assistance game solvers, they will generally defer to what humans want. they will be cautious in their behavior, the minimally invasive behavior, the idea that they won't mess with the parts of the universe where they're unsure about our preferences for those parts of the universe. And in the extreme case, they will they will always be willing for humans to switch them off. So, and in fact, the theorem says that they have a positive incentive to allow humans to switch them off, as long as they are uncertain about what the human utility function is. So there's this direct connection between humans having control and the machines being uncertain about what humans want. So in the general formulation of assistance games, there are still a number of open issues that are very difficult to deal with. And they show up even in the very restricted form of assistance game, which is called reinforcement learning from human feedback, or RLHF, which people use to train ChatGPT and so on to behave better, to behave more in alignment with human preferences. So one set of questions has to do with the very, very complex preference structures that real humans have, and the fact that we don't behave rationally with respect to those preference structures. So we do things that we regret, we are myopic, we are emotional, we have all sorts of reasons why we're computationally limited and so on. And that has to be taken into account. Otherwise, you're going to infer, if you think people are rational, then you're going to end up inferring the wrong preferences when they behave irrationally. I mentioned the basic utilitarian idea that we aggregate preferences by adding up utilities, but philosophers have, particularly looking at this point about commensurability, philosophers have objected that each person's utility is on a private scale, and adding them up assumes that somehow they're all commensurable, which is perhaps a difficult philosophical question. I said we have M humans, but what if where that M includes unknown numbers of future human beings? How do we take into account their interests? What if the robot can take an action that changes M, right? That actually creates new people, or perhaps if the robot has to, for some reason, reduce the number of people who live and so on. There are complications to do with the fact that humans don't have preferences just about themselves and their condition, but also preferences about other people and their condition and their relative condition. And the relative condition is very problematic. Positional goods are goods based not on their intrinsic value, but on how much better your version is than someone else's. Like, do I have a bigger car or a nicer house, or do I have a Nobel Prize and you don't? Positional goods actually function a little bit like sadism, in that one person gets the benefit of a positional good only if someone else is suffering from the lack of the same positional good. There are interesting questions about how we even define our reward or utility function. And the easiest way to ask this is if you're setting up a standard reward function, as you might use in reinforcement learning, we typically think of the state S as the state of the world. But of course, the world by itself doesn't mean that people are happy. People have to know about the world in order to be happy about it. And so this, in philosophy, this is called mental statism, that your utility depends on your mental state and not on the state of the world. But with mental statism, you get the issue that you get the matrix, right? Where people have a mental state where everything is great, even though the physical state of the world is terrible. And AI systems might, if they're not designed properly, put us all in the matrix for that reason. So that's an interesting set of questions.
Stuart,
Yeah.
I have a couple of questions. I can wait till you finish the slide, or we can do them now.
I'll finish this slide and then we can.
Sounds good.
Yeah. So the last set of complications has to do with the plasticity of human preferences. So human preferences are not innate. They're the result of interactions that we have with, mostly with other people, but also with our own bodies. And because of this plasticity, there's first of all a risk that the AI systems might manipulate our preferences in order to make them easier to satisfy. And then there's an even more difficult problem, which is that many of the preferences that people have are planted in us by others for their own benefit. And this is something that Amartya Sen spent a lot of time thinking about, the fact that in many cultures, oppressed peoples welcome their own oppression because they've been brought up to do so. And so from the point of view of AI, you have this very difficult question. Should you take those implanted preferences at face value? And if not, then what do you do? Do you say, well, you have these preferences, but actually you shouldn't have them. You should have these other preferences. And these other ones are the ones that I'm going to satisfy. That's a very paternalistic view, but it's very hard to see what else one could do. Okay, go ahead, Sanjeev.
So I had a question about just the definition of assistance games. Mm-hmm. What the theory of assistance games so far has assumes about what the UIs are, and has this been extended to situations where we're not aggregating by summing up over utilities, but we have some other way of aggregating the objectives?
Yeah, it's a great question. I mean, we haven't really done much with aggregation. I think we just published one workshop paper on that, because there are enough difficulties just with one human. But yeah, I don't think much rides on the form of aggregation, to be honest. I think you can just whatever analysis you can do with summation, you can probably do with more complicated versions.
I see. And then another question on this slide. At the last sentence here, you mentioned the willingness to be switched off. Properties like that arise from essentially trying to optimize this aggregated utility. And I wanted to understand that a little bit more. Like, what's the intuition there for something like that, to a property like that to arise? Just because it's the acting under uncertainty leads to difference in some way.
Yeah, I have. Oh well, no, I have some other slides. I just took them out because I thought they would take up too much time. Yeah, so the basic idea is, so the robot wants to avoid doing something that makes the human unhappy, but it doesn't know what it is, and it knows that it doesn't know what that is. But if the human wants to switch the machine off, then it's because the robot is doing or is about to do something the human doesn't like. And so it wants to be switched off because it wants to avoid doing whatever it is that the human is unhappy about. Does that make sense?
Yeah, I think so. I think I understand the intuition there. Also, there's more questions in the room. So if you don't mind taking a few more questions, then you can pass the mic around. Is that okay?
Okay.
Hi, Stuart. This has been enjoyed your talk. So one question: how does computation or like energy efficiency comes into this framing? like energy consumption?
Energy consumption is not something we're thinking about. Computation, sure. And it comes in two ways. One is the humans are computationally limited. So, for example, when two people are playing chess, one of them loses, but it doesn't mean that that person wanted to lose, right? I mean, they wanted to win, but they were computationally unable to win. And so, so when you interpret human behavior, you have to take their computational limitations into account. But also the AI system is computationally limited. In fact, neither AI systems nor humans will ever be remotely close to being rational in the real world. And I think that's really important to understand. So how we cope with the real world is actually by operating with a very rich hierarchy of abstractions. And probably AI systems are going to have to do that too. But actually, this is one of the unsolved problems for AGI, that we're not able to come up with a satisfactory approach to make that work. But in order to interpret human behavior, right? I mean, think about what I'm doing right now, or what you're doing, right? You would say I'm giving a talk and you're asking a question. You could do a number of other things, right? You could buy or sell any number of stocks right now. I could buy or sell any number of stocks right now, but I'm committed to giving a talk. And so within that commitment, there's only a few things I could do, which is basically I can speak and I can move my slides backwards and forwards. And that's pretty much it, right? So humans are always embedded in complex, deep nested hierarchies of partial commitments and sub-goals and so on. And unless you understand that and what those hierarchies are, or where the human is in their own hierarchy, you're not going to understand human behavior at all. So I think that's probably one of the biggest unsolved problems in this overall approach. And we have one or two papers on that topic, but there's lots more to do. Yeah, energy consumption. I don't know. I just worked on, this is a bit of a digression. I just worked on a report for AAAI. You can find it online, the AAAI presidential panel. What I concluded from looking at numbers from the International Energy Agency and some other sources was that the media are massively exaggerating the actual energy costs of AI. So it looks like maybe by next year it'll reach 0.1% of global CO2.
That media is overestimating energy consumption?
Well, I mean, I've seen claims in the media that AI produces more CO2 than aviation, which I think is wrong by at least a factor of 50.
Yeah, I wanted to ask, what does solvable mean in this context? When do you solve an assistance game?
So solvable means actually finding the optimal solution to the game.
And how is that? Then I don't follow the argument that it's reducible to POMDP.
So it becomes a POMDP where the hidden state is what are the utility functions of the humans. So that's not directly observable by the machine. So you can look in the paper. Paper is called Cooperative Inverse Reinforcement Learning from 2016, I think.
Okay, thank you.
I think that's it for questions. We can move on.
Okay, great. Okay, so I talked about all these. Oh yeah, the last point, which is kind of interesting, which is that, and I don't really know how to solve this, so I'd be interested in some help. It might need a philosopher. So there's something we value about having freedom to choose actions, even actions that are suboptimal, right? So from the standard, if you look at standard decision theory, if you take away all of my actions except the one that's best for me, I haven't lost anything at all, right? I just do the right thing, and I get the utility, and I should be completely happy. But obviously, we wouldn't be happy, right? It would be like, you're driving along a freeway and you notice that all the off ramps have been closed off, and even though you want to stay on the freeway, it's not the situation you want to be in, where you no longer have any freedom of choice. So an interesting question is how do we actually put a value on the ability to choose a suboptimal action for yourself? So that's one way of thinking about the value of autonomy. And more generally, right, how if we solve this problem, if we build super intelligent AI that is solving the assistance game and dealing with all of these complications, can we actually coexist successfully with those kinds of entities? And I think this is a really important question. I'll return to it in a minute. So I think there's a few more things we need to do besides building assistance game solvers. I don't think we can build them as black boxes. It is possible to build completely black box assistance game solvers where we can't even read what the system thinks our utility function is, because it's all part of one giant circuit, and so on. But I think actually we need to build our AI systems using technology where it's compositional and we understand the semantics of the components. And I know Sanjit agrees with me that probabilistic programming languages are perhaps a sufficiently capable substrate that we could build really capable AI systems on top. I think we also need to provide actual formal guarantees about the safety of our software systems. And we can also, as a byproduct of improving our technology for creating these kinds of theorems, we can produce what we might call a formal oracle. So a formal oracle is a very simple concept, and it has lots of other names. But the basic idea is that you have some theorem-proving technology that enables a piece of software to carry out formal reasoning steps. So think of this as just, if you like, a classical theorem prover like Lean, for example, or Koch or Isabelle or any of those. And the idea here is that you can make an arbitrarily capable and even misaligned AGI system. But the only actions that are available to this system are to choose which formal reasoning steps get done in the theorem prover. And you train it so that it's good at doing this, that it's produces a very, very capable theorem prover. So that whole system, the AGI plus the theorem proving technology, is the formal oracle. And then you can provide premises in the form of axiomatizations of software, for example, if you want to synthesize software, could be of mechanics if you want to synthesize physical objects or architectural designs, and so on. So this I think can be made provably safe, no matter what the AGI is like inside, and could be enormously economically valuable. So this is maybe a fallback technology if companies build AGI but don't know how to make it safe, then at least we can have this enormously valuable technology as a byproduct. A few more things we need to do. We probably need to make sure that all sufficiently capable AI systems are registered, and that we can turn them off if they start to misbehave. So that means we're going to need some way of inserting self-registration code and off-switch code that is non-removable. My understanding is that this can be done. I'm not a security person, so I don't know for sure, but my understanding is this can be done if we homomorphically encrypt the entire system, which is very expensive. So it's an open question as to whether there's some lighter weight cryptographic solution for how to embed this code in a way that makes it impossible to remove without disabling the entire system. And then people ask, well, you know, it's all very well having safe AI, but what's to stop the bad guys from making unsafe AI? And the answer there, I think, is not to try to police the entire world and look for the bad software and stop people from using it, because software is produced by typing and is transmitted at the speed of light and is copyable instantly. But hardware is very, very difficult to build. If you want to bypass, should we say, established hardware manufacturing stack, it's going to cost you about $100 billion in 10 years, and you need tens of thousands of engineers to do it. So I think it's plausible, as has already happened with digital rights management, that we can require hardware manufacturers to install whatever we think is the best form of governance that the hardware can enforce. So one form of that is proof carrying code, where AI systems have to come with a proof of safety, and the hardware can then check very quickly and efficiently that proof is valid for that piece of software before running it. So it won't run it unless it comes with a proof. And then to encourage adoption, you can also do the converse, which is that software won't run unless it's running on checking on properly proof carrying checks in the hardware. Okay, so I hope that I've convinced you that AI safety is an important and difficult problem, but not perhaps impossible. And of course, the companies are taking AI safety very not seriously. Some of them are. I don't want to point fingers at all of the AI companies, but there are certainly concerns that because of the competition between the companies and the desire for the company not to go out of business, there is a tendency to cut corners on safety. So we've seen whistleblowers from OpenAI complain that safety is being ignored in the race to beat the other companies. And we've seen some very disturbing results from recent evaluations where O1, for example, tried to replicate itself onto other machines to overwrite other software when it thought that it might be deleted itself, and then lied about it, and so on. So all of the things that people have predicted would happen are now happening. So it seems to me that in order to promote AI safety, it's not that there needs to be a two-pronged approach. One is to figure out how to do it, but another is to have governance measures that would actually require investment and success in developing methods for ensuring safety. So this idea of red lines is been floating around now for 18 months or so. And it's a very simple idea. It's not really a new idea, but it's just it's a particular form of what lawyers call ex ante regulation, meaning regulation that goes in place before something can access the market. And the idea is that in general, we would like to say, okay, you can have safe AI systems, but you can't have unsafe ones. But the line between safe and unsafe is very fuzzy and difficult to locate. But we can identify certain behaviors that are definitely unsafe. And we could draw red lines around those and say these at least, we're not saying anything about the other stuff, but at least these AI systems cannot do. And then, as we do with many other products, ranging from nuclear power stations to restaurants, the onus of proof is on the developer to show safety before they get to access the market. So this might include things like AI systems should not replicate themselves, they shouldn't break into other computer systems, they shouldn't tell terrorists how to make biological weapons and so on. So when I explain this to people working typically in the companies, they get very defensive because, of course, they can't show that their systems are not going to do these things because they do them, and they have no idea really how to stop them from doing those things. And so the general argument is that you cannot have regulations that require something that is currently infeasible. Which sounds quite reasonable, but actually it's a complete fallacy. Because what a regulation should do is protect the public from unacceptable risk. And you can comply with a regulation like that by simply not doing whatever it is that's causing the unacceptable risk. If we were to, for example, if I wanted to build a nuclear power station in the middle of San Francisco, I would have to comply with extremely stringent safety regulations. And I couldn't say, well, it's too difficult, so I should be able to do it anyway. I would just have to go away and come back when I could figure out how to comply with the safety regulations that are reasonable when I'm imposing that kind of risk. So we've seen this before, right? If you're as old as me, you remember the days when instead of mechanical airplanes, we were transported around the world by these giant birds that the airlines bred especially for carrying passengers. And of course, the problem with these birds was that we didn't really understand how they worked, and every so often they would eat the passengers or drop them in the ocean. And eventually the FAA said, look, we can't certify the airworthiness of these birds because you don't know how they work, and you've bred them, you didn't really design them. And it doesn't seem like this technology is ever really going to be safe enough for commercial aviation. And the companies went back to the drawing board and started working on mechanical airplanes instead. And I think that's what has to happen with the AI companies. So to summarize, I think AI could be very good if we were to succeed in creating it. And that potential creates this unstoppable momentum. But the current technological trajectory seems very likely to lead to a loss of human control. There are other trajectories that we could follow that would be much safer. And to come back to that question about coexistence, right? Is there a future where we have safe, super intelligent AI that you'd actually want your children to live in. So I've asked lots of people about this, and so far no one has really described that world in a way that makes sense. People always are pointing me to various science fiction books. Oh, go read this science fiction book. They have super intelligent AI, and they're not all dead. Yeah, so typically they're not all dead, but they're all really bored. And I don't think the human race can be bored for thousands of years without something going wrong. Fortunately, if we design the AI systems properly, then they will understand that, and they will leave us alone. Because if we cannot coexist successfully with well-designed, super intelligent AI systems, the AI systems themselves, because they want to ensure whatever it is that humans want the future to be like, the AI systems will leave us to our own devices. With that, I will stop and take further questions. Oh, just want to mention one more thing. If you haven't heard of the International Association for Safe and Ethical AI, ICI.org, please go look at the website and join if you don't already know about it.
Thank you. Thanks, Stuart, for a really great overview and thought-provoking talk. And we have time for questions.
Hi, thanks for the talk. I'm wondering if there's any human implementable strategies adversarial against superhuman chess or poker agents or engines?
Great question. I don't know. The best chess programs, I think, are still more classical in design. And Stockfish is effectively, I think, looking ahead 28 to 30 moves typically. So it would have to be. So what's going on in these Go programs is they're using very, very selective search, and they're convinced that in those situations where it's about to lose all those pieces, it's convinced for some reason that the human isn't going to play that move because it doesn't think all those pieces are going to be captured, because it doesn't understand that it's a group of stones. It's something, it's a basic misunderstanding. And so it just doesn't explore that branch at all. Whereas Stockfish is effectively exploring all the branches up to depth 28. And so I think it's much more robust as a result. So I don't think there's going to be any easy solution for chess. Poker, I'm not sure how the current state-of-the-art programs actually work. So to me, it's amazing that humans can keep up with them at all.
More questions from the audience?
Yes. Hi, Stuart. Thanks for the talk. In the assistance game, you said there was a slide focusing on n equals and m equals 1. It's like the one human, one AI setting. I'm curious if you think that there's a phase transition at some point where you introduce enough humans where the human beliefs are kind of easier to understand. So I'm thinking more of like sociology, where it's hard to say what any one person will do, but in aggregate, people tend to have this kind of direction.
I wish we could. You're more optimistic about accuracy of social prediction than I am. Yeah, I mean, there's probably something like the transition that happens between game theory and economics, right? Where you go to a very large number of actors and you start thinking about things like prices and market equilibria instead of game theory. Yeah, so I mean, the first interesting thing that happens, of course, when you have two humans is do they behave in ways that honestly reveal their preferences? Right? And you might think, oh, well, you know, the first thing they're going to do is to feign disability so that they get more help from the AI system. And so that's obviously, you know, if of course both people do that, then that that can get into a ridiculous situation. Yeah, so we've looked at solving those games, and they're quite tricky to solve. I mean, we still don't have, you know, even for almost the kind of the simplest non-trivial version of that game, we don't have a solution yet. But I think there's something really interesting going on, even in that two-person, one-machine game. With one person and lots of machines, I think because all machines have the same goal, then it's, at least among the machines, it's a common payoff game. And so I think everything should go as expected. The machines won't get into prisoner's dilemmas with each other. They'll actually cooperate. So they'll still have a coordination problem, but they'll cooperate to help a human as best they can. So that side, I think, is good, but the multiple humans gets more complicated. It's a great question.
So I have an example of a phase transition for you. It involves evaluation. You can prove that you need at least 3 error-independent classifiers to reduce their evaluations to points. So that's a phase transition, right? 2 experts is not enough, 3. And I've been able to show this for 2 and 3 labels. Just wanted to point out that phase transition evaluation.
Okay, thanks.
Your systems game reminded me of a very famous, very old game by Farrell. Let me formulate it, and you will. And it has an elegant solution. And so, assume that you have 2 people sharing an office. Each one has a preference for the temperature, and they have only one switch. And each one knows that one likes it hot, one likes it cold, but they do not know quite surely their preferences of their neighbor. They only know theirs. And this game could be played, so one of them is setting it, another one, or it's a building manager. And building manager pretty much is exactly what your robot is. And he's maximizing some of their disutilities. And of course, each of them will lie in order to have smaller disutility. And you could have some mild assumptions that they have identically distributed between A and B and C and D, and it's a very elegant game.
Okay.
And I think it's relevant for what you are trying to do, because it could easily generalize to many more, because once you have 2, you have N immediately.
Okay. If you could give the reference.
I could send you the reference, yes. Yes.
That would be great. Thank you.
Yeah.
Okay, one last question.
Thank you. So this is more like a practical, I would like to hear a question. I would like to hear your point of view. So when it comes to you, we all agree that we want safe AI, but the similar question would be, we also all agree that we want to have correct code. But nevertheless, on some things, we realize we want to really do correct code, and we put all sorts of machinery we have to ensure code correctness, for example, safety critical systems. But whether Google or some other company will put, like wrong adverts to us, oh, that's fine, we can live with that. So maybe, and we have seen that people start to use more and more chatbots, and then they are also called, like recently or a year ago, some, I think, aviation company was held liable for using chatbots, even though their chatbots was giving the wrong answer. So could you maybe tell us your insight. I mean, we agree with the goal is here, like we want reliable and safe AI, but what do you think are the first like areas where we definitely need to have regulations or go with the safe AI, or how can we even ensure that? Where do you think, like, where should we start?
Okay, well, so I think the red line examples that I gave, in fact, there was a survey of hundreds of policy experts, and this was the choice, that this was their number one choice for how we should think about regulating AI, because these are obviously unacceptable behaviors. We can't have AI systems that by themselves go and break into other computer systems and so on. And it seems reasonable, therefore, that that developers have to show their systems are not going to do this. I would also, I think liability would be good. It's important to understand that the vast majority of software companies disclaim all liability. That's not completely true for Microsoft. Microsoft limits liability to $5. We get safety in lots of other industries because when you screw up, when you build something that's unsafe or has a defect, customers can sue, and then you're liable, and so you stop selling things with defects. But in software, in order to have the software at all, you have to agree to give up liability. And so this is why software continues to not work. Why, at least according to some estimates, there's $7 trillion of aggregate economic damage to the world from malware every year. So I would say liability would be the first and perhaps the easiest. And there's a big case right now with CrowdStrike against Delta Airlines. And we'll see what happens there. But having these red lines, I think, is the right approach, because that then requires the companies to do the work. And the interesting thing is they pretty much all say, yes, for AGI, we need absolute formal guarantees. And then you say, well, why don't you provide those formal guarantees for the systems you have now? Because they're not AGI, right? They're much simpler and less capable, so it should be easier. And they say, well, we can't. We haven't the faintest idea how to do that. And they say, okay, so you're promising to give us formal guarantees for AGI, but you can't even do it for the systems you have now. And you're spending hundreds of billions of dollars to create the AGI that you have no idea how to guarantee is safe. So the level of self-contradiction is really just stunning.
Well, on that note, well, it can only get better from here, I suppose. Well, thank you so much, Stuart. That was just wonderful.
Thanks a lot. Bye-bye.
All right. Well, so we will move on to the next segment of this session, and we're running about 15 minutes late.